All right, so welcome to the beginning of the first term on this seminar. We are happy to have Andy Drucker from the University of Chicago that will tell us about games against nature.
Thank you, Avi. Thank you very much for the invitation to speak, and it's good to be back at IAS after a fashion. Hope you're all doing well. So just testing the setup. All right. So yeah, it's a long title, and I'll try to break it down bit by bit and introduce the subject appropriately. First, I'd like to thank Rahul Santanam of Oxford for supporting this work in several ways and for many helpful discussions along the way. So,
sorry, can you make it full screen, the slides?
So it looks partial screen to you too? Okay, let's try that. View mode, full screen. Is that better? Is that
still the same?
The same.
And
all right.
Change if you remove the the view of participants, Moni, you don't get the full thing.
Well, it's still like in the anyways.
Well, something like unselect the toolbar in the view or something like that, but not sure.
Yeah, so I have struggled with this. I don't know that unpin command bar. Is that better? Did it get bigger? Okay,
yeah, that's great.
I think that's the best I can do, but hopefully it's big enough. If I then enter full screen, I can't see you, but I can. Okay. Is this? Shall I go?
That's good. I think it's okay.
Okay.
You can see us, Andy?
No, I can see you now. If I go into.
Okay, so that's okay, excellent.
Now I can't see you. Is that any bigger though?
No, go back to the other way. Yeah. It's not worth it.
All right.
It's the same, actually.
Sorry, folks. All right. So I'm going to begin with games, just games, and we'll get to fully alternating and games against nature, and then we'll take it from there. So I'm going to begin with the general notion of fully alternating binary games. And these are two-player games in which we have players, I'll call them P1 and P0. And they're going to choose binary or Boolean moves, X1, Y1, X2, Y2, and so on in that order. Player 1 being responsible for the X and player 0 for the Y moves. And throughout this talk, I'll use the perfect information setting, right? So this concerns perfect information games. Each move of each player is made with full knowledge of previous moves, although not future moves. Okay, so the outcome of the game for a given set of moves is given by a payoff function for player 1. So this is for starters, we could say this is a Boolean function, which says for any sequence of moves who wins. You can also consider real valued payoffs. And later on, I will consider real valued payoffs in the range 0 to 1. So the computational problem that we can associate to this is given f in some way, how are we to determine the value of the game for player 1, where value is interpreted appropriately? Okay, but first, how are we given f?
So just a second, interpreted appropriately is that P1 would like to maximize it, the maximum of this value.
So player 1 likes getting payoff, so it's a payoff for player 1, and player 1 will always be maximizing in this talk. Player 0's role is I'm going to talk about two settings for player 0's role. Okay, so how is f given? Well, as in many problems in theory of computation, you can study the black box setting where f is just an oracle that you can make queries to. And you can study the white box setting where f is described typically very succinctly by a circuit, right? Where you input but you see the operation of the circuit on these input bits x1 through yk. Okay. So
this is a good example.
Sorry?
Chess is a good example.
Chess is a good example, except for the fact that it's not binary. But you can keep in mind, these are, yeah, I mean, the paradigm for this type of work and part of the classical motivation was to play chess on computers to develop chess AI and for other similar games. Okay, so what do we mean by the value of the game for player one? In the classical and best studied adversarial zero-sum version of this problem, player zero is trying to minimize and is playing, let's say, optimally to minimize. And then under optimal play, the value should be defined as this alternating maximization and minimization expression over the base formula F. And hopefully this is familiar in some form. It can also be represented using ORs and ANDs. So OR equals max over the Booleans. Okay. So what is known about the complexity, the difficulty of this problem? I'm going to talk a little bit both about the black box and the white box setting. Of course, there's some relation. So it's a classic result that this problem is p-space complete if F is given succinctly by a circuit. So this leads us to suspect that it cannot be solved in time polynomial in K if P is different from p-space. But more strongly, as far as we can tell, it seems to need time which is exponential in the number of moves. So in n or 2 times k to evaluate. But we at least know that this problem is solvable and faster than naive brute force search. And this is one of the original drivers of progress in AI and in game playing software. And some of the ideas existed, before these two works that I cite here in terms of like pruning techniques for and/or max-min evaluation. But Sneer gave the first what I would call a worst-case runtime improvement for this problem with a randomized algorithm, a simple randomized algorithm. And Sachs and Wigderson optimized the analysis, showing that you can evaluate these games with a number of queries to F, which is exponential, but an improved exponential. So 2 to the 0.753 n. This is an explicit constant that you can work out. So it's a simple recursive evaluation algorithm, and this is part of the bedrock of classical game playing AI. And let me also mention that in the black box setting, this problem is very well understood. So the main contribution of Sachs and Wigderson was to show that for zero-error randomized algorithms, this is as good as you can do. So the runtime achieved by this simple randomized algorithm, which I'm not going to present, is a provable limit in the query complexity or black box setting, at least for classical algorithms, quantum being able to get down to 2 to the n over 2. And Santha showed this for the two-sided error model. Okay, so that's the adversarial picture, pretty well understood. So our study is where player one is, as before, a maximizing strategic agent. And I'm going to use W for player one's moves now, although we're not going to do this too much. But I want to emphasize that player zero now is going to play moves Ri, where the R stands for random. So player zero's moves are now uniformly at random. And following Papadimitriou, we think of this player as an indifferent nature who's just, blowing with the wind and doesn't care about the outcome. So, and Papadimitriou studied the complexity classification of such games where the value has been redefined suitably to model this totally different form of player zero. So this can be said to be a fairly general expressive model to describe any kind of ongoing interaction with physical or other systems, nature being the physical or other system, as long as we have some kind of reasonable statistical description of its behavior. So we can't predict what nature is going to do several steps ahead. We can't predict the weather, say, but we have some kind of reasonable statistical description of it, so that in the simplest case, if we model its successive moves, or which you can also think of as new observations of an unfolding state of nature, if you think of these as being uniform, we're assuming that we at least have some confidence in the distribution on these outcomes. And the restriction to uniform sounds somewhat severe. Let me just say that it's not quite as severe as it sounds, because we know that with uniform random bits, you can sample many other bits. You can sample many other distributions, rather. So one can also imagine setting up games in which some kind of a generator is packaged as part of the game description, and this can express certain other distributions on how nature unfolds, possibly affecting the length of the game. So that's just something to keep in mind, and some motivation for this particular focus. All right, so here it's appropriate to define the value as this alternating maximization and expectation, or averaging, expression. And so we see now that this is going to be a real value quantity. And what do we know about the complexity of computing these values? Well, they're also p-space hard to compute, and basically p-space complete. That's the correct classification. Papadimitriou showed this for various games, that it's hard to decide whether its value in this sense is bigger than a half or less than a half. And then a few years later, building on our knowledge of the interactive proofs model and this beautiful sequence of results showing the expressive power of interactive proofs and the result IP equals p-space of these authors, it follows that computing these values even approximately to within plus or minus a third, say, is p-space hard. Okay, so let me just say briefly for review purposes, although it's not necessary to understand this for my talk. So interactive proofs are protocols in which we have some computational question that we're interested in the answer to, and basically we re-express it in terms of a game against nature. And so membership or non-membership, for example, in a language, L, can be re-expressed as a certain game like this, whose value is either high or low, depending on whether X is in L or not. And then by watching a computationally powerful but untrusted prover just play this game successfully, that can convince us of the truth of an assertion like X is in some language. So because of the expressive power of this problem as a target for reductions for all of p-space, it follows that even approximate evaluation of these things is p-space hard.
Can I say an interpretation of this result that I like in the language of games? So for people who didn't see it, this IP equals p-space, so approximating the value of such a game being so expressive can mean the following, that if some alien landed from Mars and claimed to have found a winning strategy for chess, let's say as white, he can convince any of us of this fact beyond any reasonable doubt just by playing against him. Only the cute or deep phenomena in the proof is that instead of chess, we will be playing a game in which the optimal strategy for that alien is just tossing random coins. And nevertheless, there is some completeness result here, that if he can win against this strange game by playing randomly, he could win in chess by playing optimally, if and only. So that's a remarkable fact. So it's amazing that playing games stupidly can be as optimal as playing, perfect.
So I think in that scenario, as I understand it, the alien still needs to play intelligently, but we don't need to. We don't have to worry about the fact that we're not very good at chess. We can just play randomly, and then the alien's victory under those conditions convinces us.
It's the alien that, I mean, we play as cleverly as we want. It's the alien who plays randomly, but the translation to the game in which optimal strategy for the alien is random is what needs cleverness. But this translation is known to all in this paper.
Okay. Yes, I think we agree. Yeah. I mean, another way that you could think about it is that like solitaire games are surprisingly rich. So if your internet connection is broken and you don't have a good chess opponent, you can play against a source of random bits and still have all the entertainment and all the intellectual challenge of these types of games. So yeah, a very rich set of results and perspectives. But let's see. Let's go on. So in addition to the theory of computation and complexity perspectives, let me say that this type of alternation, this type of scenario has been studied in decision theory, control theory, AI, and related allied areas like this, near engineering and automated reasoning settings. So in terms of what is understood there on a theoretical level, well, the best understood model for giving algorithms with provable guarantees in this type of framework is that of Markov decision processes, or MDPs. So this is a classical type of framework used whose algorithmic potential was already understood by Papadimitrio's time and goes back to like the early days of dynamic programming. So let us imagine that the game we're playing against nature. So we're playing we're a player one, a strategic maximizing player, and we're playing these moves WI successively, and they're followed by these interjections of randomness RI. And let us suppose that there's some relatively small or simple system state whose state is evolving in response to these updates given by our moves. And then as we go, we are incrementally given some form of little payoff, depending on what the current state looks like. Or maybe the payoff comes all at the end, but that can be incorporated into this framework. So we imagine that there's a small payoff determined by the current state, and then the overall payoff is just the sum of payoffs over the stages. So a pretty natural framework to express different things, and there's a dynamic programming approach to computing the values whose complexity scales gracefully, polynomially, with the number of states of the system. So this is nice to know. And let me just say that, that my emphasis in this talk is on pushing the envelope with games where the state space is not small, but it's explosively large and is potentially on the order of the same size of the game tree itself. So a game like chess has a number of distinct possible states that is large even in comparison to the number of possible game histories. So let's just keep that setting in mind. Questions about this? Okay. So this problem has also been studied in the setting when f is described by a Boolean formula. So this is a potentially much more expressive framework called stochastic satisfiability in some papers. So Littman, Majicek, and Tony gave several algorithms for this problem, including one that has a rigorous improved runtime guarantee to estimate these values for certain alternation patterns. That is, patterns of player move order, in which, by the way the moves are staggered, there are not too many truly distinct player one strategies. So just as an example, if instead of the fully alternating setting at the top of the slide, we had the case where all of the player 1 moves were in advance, happened first, then there would only be 2 to the k strategies. That's just an example of the kind of limitation that comes as a function of move order. And in such settings, there is a sampling base. They give a sampling-based algorithm to actually estimate the payoff to every player 1 strategy and then select the best. So sampling ideas can attack this problem successfully, as these authors show. But this is not directly successful on the fully alternating case that is my focus. And they give other algorithms also, and they and other authors have investigated this experimentally. And Tony, feel free to comment or elaborate if anything I say is off base, or there's more to be said.
No, sounds great.
Okay. So let me mention that more recently, it's been shown in the course of studying the so-called longest common subsequence problem. You're given 2 strings, and you want to find the longest subsequence, which is common to both of them. This problem, has been intensively studied, and in the course of trying to show that it's hard, actually, Abood and Rubinstein have shown that there's a reduction from games against nature to this problem, an approximation-preserving reduction, in fact. And by mimicking their steps, one can also show such a reduction for the longest increasing subsequence problem. For a single list of numbers, find the longest increasing subsequence. So these are good reductions to know, and they lead to well-studied problems, which, however, seem to be more difficult in certain ways and meaningfully different from the source problem. And let me just say that the known algorithms for these problems, although they're sophisticated, they don't give interesting results in the setting that I'm looking for. Okay, so the best kind of thing that they can show is that if you, for this type of value as above, if you want to give a p approximation to this value, you can look at a p fraction of the table for f. So this is a nice observation, but it's also something that can be observed directly without this kind of reduction. Okay, so in summary, what remains open from after all these various sorts of papers is whether there's some sort of algorithmic improvement that's akin to or resembling the ones given by Sneer and Sachs-Wigderson for these games against nature. And that's what I do in this work. I say the following. There's a randomized algorithm whose input is a payoff function, f, as described. The algorithm makes an improved exponential number of queries. All right, so n is the number of moves, 2 to the n is the table size for this f. We make 2 to the 1 minus delta n queries to the table. All right, delta is a small but absolute constant. And our output is a lower bound, a certified lower bound on the value of this game as a game against nature, which in expectation over the randomness in our algorithm is exponentially close to the true value in additive distance. Okay, so comments. This works equally well with bounded f, not just Boolean f. The boundedness here is essential because if f was unbounded and was allowed to have certain huge values, then a single table entry of f could contribute most of the value, and finding it would amount to a needle in a haystack problem of the sort that we know that for classical algorithms is hard and requires brute force, essentially. So I hope that's clear, that we need boundedness here. Also, so I state the algorithm as outputting certified lower bounds on the value, but it essentially does so by discovering strategies. So this algorithm naturally is adapted to give near optimal strategies. And this is not by appealing to a generic search to decision reduction of the sort that you see for NP problems. It's not quite so clear how that would work here. It's more that it's directly the approach yields near optimal strategies.
So Andy, before this result of yours, the best bound was just 2 to the n, the brute force on this general setting?
Yeah, I believe so. Okay. So
just a minute.
Yes.
What is the difference between that and the, let's say, Sneer and the Sachs we're using?
Well, this is to compute the value for games as a game against nature. So it's to compute this alternating max and average expression on the input f. Their algorithms are computing the value as an adversarial zero-sum game. Okay. So this is a potentially much, so.
Well, it's incomparable, right?
It's incomparable, yeah. So there's one sense in which, there's a natural sense in which it can be compared. That is, if I can achieve a value of v against a perfect opponent, if I can get value 1 against a perfect opponent, I can certainly get value 1 against a random opponent using the same strategy. But my work and on all work in this area it really aimed at saying, well, we know that nature is going to behave in this random way, or we have a probability distribution on nature. It's not adversarial. It's not trying to mess us up, and we want to exploit that as much as possible. So if the input was a chess board and you have, you know, 1 king and 1 pawn against a huge army, you know, we're actually trying to use the fact that nature is just going to be moving their pawns at random, and we want to say, well, I've still got a chance. Even though a good player could demolish me in this setting, I want to fully exploit my assumption that the opponent is playing, you know, fully randomly. So a different computational problem. The results, there's no direct, as far as I know, there's no direct implications in either direction for the algorithmic problems. Okay. So I want to mention caveats or downsides. The error, as you can see, is small, exponentially small. But let me just emphasize that the guarantee is additive and not multiplicative in its nature. So we're not getting a 1/2 approximation in the sense of the most typical language used in approximation algorithms. If the value of our game is exponentially small, we're not necessarily finding or realizing that value. But as long as the value of the game that we're studying, that we're given, is non-negligible, then we can harvest or achieve almost the full value. And I think that that's satisfying enough, given that usually when we play a game against nature, we're doing it because we hope to realize some significant value. Now, a more significant downside, 2 of them, are that, first of all, the delta in this exponential savings is, at least currently, tiny. All right, so I haven't optimized it, but it's very small. And to briefly, you know, telegraph why this is, so like Sneer and Sachs-Wigderson, my algorithm is recursive. The form of the recursion is different, but it's recursive. And the strength of a recursive algorithm is typically comes from how strong the algorithm is doing on a certain base case of constant size. So in Sneer's algorithm, the base case is on k = 2, and you're seeing some noticeable improvement on a game tree of 2 layers. And on mine, the base case has to be very large to do some of the analyses and get the ideas involved to work. So it's coming from a base case which is not as efficient as that in the earlier works. A more significant downside, I think, or one that maybe has more lasting, is worrisome in a more lasting way, is that the algorithm is exponential space. And this stems from the fact that the form of recursion is different, and rather than doing sequential recursive evaluations, we're actually maintaining parallel recursive evaluations that are being staggered in some adaptive way. Okay. So A first step towards talking about what we do is to take the so-called max average formula perspective. So MA here stands for max average. And this is a sort of standard in this area form of translation. So define a function on real valued inputs, which applies an alternating maximization and average formula of height 2k to a real valued input vector of length 4 to the k. Here's an example with k equals 2, n equals 16. So the m gates are max gates, the a gates are equal averaging gates. So this is a real arithmetic formula. Even if the inputs are Boolean, the output will in general be real. Okay. In this revised perspective, our goal is for a given input vector to approximate the MAK value, the output value, with a small number of queries to the input. And now small here means capital N to the 1 minus delta, where capital N is the full input size. So this X now is standing in for the function table. And the individual gates in this picture correspond to initial sequences of play in the game. So for example, the output value of this formula is going to give the max average value of the full game as a game against nature. If I look at the left A node here, its value is going to be the value of the game against nature conditioned on player one's first move being a 0, let's say, and so on. So there's a natural correspondence, which I invite you to verify or look into, but we're just going to switch over to this perspective because it's convenient. Any questions about this? So we'll see this picture, this kind of formula again. Okay. A simple example, you can just quickly spot check that you understand how the gates work, but this is just a worked example. Okay. These are evaluations of real gates. Okay, so in terms of basic ideas used in this work, I want to start with the notion of certified lower bounds for this max average function. So let us say that we have only looked at a subset of the inputs to this MAK function, as in the picture. Well, we at least know that this formula is a real monotone formula. So you can get a certified lower bound just by plugging in zeros for the unseen inputs. We're assuming that the inputs are bounded in 0 to 1. So here's such a lower bound. And every certified lower bound that I work with in this work is of this form. So if you look back to the slide stating the theorem, the certified lower, the output V prime is going to be as determined by one such partial view.
Sorry, do you mind repeating? I got an unfortunate call just at the minute.
Oh, no
So
worries.
the definition of certified lower bound. Could you just say it one more time?
All right. So if you see the picture here, we have a partial input to the MAK formula. It's actually the same input as in this picture. So the true output is 0.55. But so far here, we've only seen these 4 inputs. And what I say is that just by plugging in zeros to the unseen coordinates, we get a certified lower bound. And evaluating that, we get a certified lower bound. In this picture, you can see that it's actually just a single one of the seen coordinates that's causing this certified lower bound to kick in.
Yeah. Okay, great.
All right, sure. Okay. The second basic idea that we'll be running with throughout is the notion of an all queries algorithms. So our ultimate goal is to design algorithms that make few queries and then halt with an output. But in the course of building them, we're going to need to build progressively stronger algorithms for progressively larger and larger input sizes. And our initial stages will be quite modest. And it's also going to be the case that we are, so unlike in the SNEER approach, where the recursive calls are made and then they halt with an output, these recursive calls that we're going to be making are going to be ongoing, and we're going to be getting information out from them, which we are then going to be using to decide which of our recursive calls to drive further, to progress further going forward. So it will be essential to us that we have this ongoing view of these recursive calls. And to study this and to talk about this, it's natural to actually talk about basically all of the algorithms, the query algorithms that we develop, as all queries algorithms. So they're all assumed to make all of their queries, n queries, in some order. And our chief concern is in their progress over time for a given execution. So I've drawn a graph here. And we see, so this is just a picture of a particular execution of our randomized algorithm. So I graph the number of queries, and as a function of the number of queries, I say, how well is the certified lower bound that we've exhibited so far doing in approximating the true MAK value? So initially, our approximation error, or what I'll call defect, is equal to the MAK value, because the true value is MAK of x, but we've looked at nothing and we've certified 0. So we have that gap. And then as time goes on, we get progressively better information. And eventually, after all n queries, we've seen all of x and we've driven the defect down to 0. Does that make sense? So this will be basic, and I'll use this notion of defect going forward. Okay.
So just a question, general question. Is this fair to compare it to branch and bound algorithms in optimization, where you explore more depending on the estimates you have for this optimization problem?
I think that that's broadly fair as a comparison. Whether the degree to which it fits a certain branch and bound paradigm, I would have to look into and get back to you. Yeah.
Okay. The other question is that the source of the lower bound in my work with Mike Sachs is basically proving that looking at the inputs in a particular order is an optimal way to compute the value in a circuit which is n's and o's, not n's and average, but in a Boolean circuit. And so an optimal strategy is one which fixes the order in which it queries inputs, unless it would skip any if it knows that it will not give a better lower bound. That's the only thing that the algorithm has to do. It seems that in your case, you may have to revisit a decision not to query. So it's not a directional algorithm as we.
No, it's not a directional algorithm. And I don't know that such a thing. So I don't have any form of algorithm which I conjecture optimal, I guess it's fair to say. Though I certainly invite people to try. But there's a greater difficulty in this setting, I think, of ruling out certain inputs as being irrelevant. Okay. I mean, broadly speaking, it's difficult to do confident pruning, let's say. So there's no notion of domination of strategies for our opponent. Just because a certain way of playing for the opponent is better than another for the opponent, we can't say which one they're going to use. Okay. All right. So our ultimate goal is a picture like this. We would like for a small epsilon less than 1 and a small t much less than capital N to say that there's an expected defect bound of at most epsilon that holds for all inputs x when you look at the picture after t queries. Hopefully that makes sense. That's what our goal looks like. What we will actually do as a stepping stone to that is to give algorithms that have more modest bounds, more modest defect bounds, but as a trade-off in return, what we're going to do is we will be more careful about measuring their expected progress at different moments of time. So what I have here is a profile where I say that for a given algorithm that I've defined, its expected defect after t1 steps is at most this epsilon 1, t2, epsilon 2, and so on. So I have these 3 data points that come from an analysis of this algorithm. And you can also, we always think of them as being supplemented by the trivial estimates at the endpoints. So So our pictures, our analyses will be of this form, and they will give a progress profile over time. And time will be divided into epochs for these algorithms. So there will always be an epoch 1, an epoch 2, and so on, so ultimately the number of epochs, as you see, is one larger than the number of these interesting intermediate step guarantees. So when I say epochs, I mean that time has been artificially divided by the designer into these specified blocks. And as in the picture, these blocks are generally not going to be evenly sized or spaced. So that's terminology going forward, and that's our perspective. Okay, so as I say, the algorithm is going to be recursive. We need a notion of composition that's appropriate to our goals and to the way also that we analyze these algorithms. So our composition looks like this. So I'm picturing a large general input size as being of index k plus L. So L is going to be the top part of this MA tree and K the bottom part. So we have subtrees of size 2K. And we assume that we've already inductively built an algorithm for that input length, 4 to the K. Call it the inner algorithm. So it's capable of working on these subtrees, which we see in our larger input size. We also have an outer algorithm, call it QOut, for the problem MAL. So it's going to be sort of handling the top level view of the MA tree and the inner algorithm, the bottom levels. The outer algorithm is of a special type that I'll discuss shortly. So the composed algorithm is going to maintain parallel simulations of the inner algorithm on each of these height 2K subtrees. So there's an outer executive algorithm, which is maintaining these inner parallel simulations. So I'm just using here xi to mean the ith block of the input according to this natural partitioning. So in this work, this L is a huge but constant value. This L is the base case. So the outer algorithm is going to be a fixed base case algorithm that we design. The inner algorithm is going to be the result of recursively building it up to this level K. So here, K is a larger value and it grows with recursion depth. I hope that makes sense. But I guess our fundamental view is top down in this picture. So the composed algorithm is divided into phases, and these phases have subphases. In a basic step or subphase, we use the outer algorithm to choose a next index, a next block, and we are going to advance the simulation of the inner algorithm on that subtree by one whole epoch. Okay, so now let me note here that the notion of epochs, these epochs are used in our progress profiles for algorithms, so they're part of our analysis, but they're also structuring the recursion itself. So they're also part of the algorithm. All right, and in phase R, what we're going to do is have all of the subtrees complete the rth epochs of their inner algorithm computation in some well-chosen order. But let me know that this is a limited form of adaptivity because if the inner algorithm has a certain number of epochs, we're going to pass through successive points in time where we've equalized the number of queries to all of the subtrees. So this means that even though we're doing some adaptive things, it's a controlled adaptivity, and it doesn't lead to runaway situations where one of the subtrees gets all of the queries. So here's just a picture. The outer algorithm might choose this subtree and advance through epoch 1 on this subtree with the inner algorithm. And then this one, until eventually they've all advanced through epoch 1. And this is said to be the end of phase 1 for our composed algorithm. We do the same thing for epoch 2 in some chosen order. the outer algorithm has a specific and limited viewpoint during this process. Namely, it's only seeing certified lower bounds from these inner subtrees. So initially it sees the values 0, which are the certified lower bounds so far, which are trivial. It's using these numerical values to say, I want to make my next investment in this subtree, and it yields some improved certified lower bound. And then potentially based on what it sees there in terms of this number, it's going to say, oh, I want to look at this subtree. So it's only using these old and new values to drive the choice of the next subtree to look at. And this is going to be done phase by phase, and every phase is handled in the same way, actually. Okay, so we said that epochs are central to our analysis, and they drive the form of composition as well. What form of epochs do we use for the composed algorithm so that we can transfer, quality guarantees for the smaller inner algorithm up to the larger one? Well, it turns out to be appropriate to end epoch 2, for example, not right when phase 2 ends, but midway through phase 2. And in fact, most of the way through phase 2. So there's some critical moment during phase 2 when most, but not all, of the subtrees have advanced through their second epoch, where I say this is the time when I should mark the end of the second epoch for the composed algorithm, and when I hope to be doing pretty well. So it has to do with the fact that our outer algorithm is doing something adaptive, and that it's timing things so that at this moment, it hopes to have just made a clever choice, so that it's making progress a little bit faster than you might naively expect. And so it's at that moment that it says, because I feel confident now, let's do the analysis at this moment. Okay, so.
A question. What I gather from this description so far is that there's this outer algorithm that's trying to evaluate a small game tree, only the values are not there yet. It's going to gather various certified lower bounds on them. And it tries to get better and better approximation, or or more confidence of the lower bounds and their value to the final value of the game by sort of querying them for longer and longer periods, but also determining which it's going to query longer, and gathering enough information. Maybe it looks like they are concentrated, or it's clear who the dominant one is.
Yeah, so part of the reason that I end epoch 2 midway through, but really most of the way through phase 2, is that I've gathered enough information to make a single but confident adaptive query. Yeah. Right. So definitely, and I think everything you say there is accurate. The epochs don't get longer. Well, the relative length of the epochs is a little bit complex to describe, but yes, the epoch endpoint is carefully chosen to reflect an adaptive query at a critical moment when we've gained enough information to do so with some confidence. Okay, so how do the epoch defect bounds for the smaller inner algorithm induce new ones for the outer algorithm? This is going to depend, of course, on the details of our outer algorithm. But first of all, in order to facilitate comparison of smaller and larger input sizes, it's helpful to switch from number of queries over to fraction of queries, because this is something that always ranges from 0 to 1, and we're always trying to look, to get a small fraction of queries doing well ultimately. So the old defect bounds become these new defect bounds re-expressed in terms of the fractions. And I'm going to suggestively kind of draw these lines, suggesting that there might be some kind of interpolation happening as we progress most of the smaller algorithms from their rth to r plus first stage. So just concretely and naively, let's look at the second epoch of the composed algorithm, where we started off in the position where everyone had finished up their first epoch, And there was an epsilon1 goodness associated with that first epoch. So the inputs at that stage were epsilon1 close in expectation to their true values. Now, a basic fact about MA formulas is that if the inputs are epsilon1 close in expectation to their true values, then the output will be epsilon1 close in expectation to its true value, or better. So you can definitely expect to inherit the epsilon1 goodness after the first phase. But now after the second epoch, we've advanced some, let's say 80% of our inputs from being epsilon1 good to being epsilon2 good. Well, naively, we can at least hope for the output to obey a 0.8 weighted average of these two guarantees, as in this picture. So I'm saying, roughly speaking, this looks like 80%, and that's the epsilon prime that you would hope to achieve. And this, it's not hard to achieve this. So this is something attainable, but actually this idea is not strong enough, and it doesn't lead to good algorithms.
You really need to multiply your epsilons by some fixed constant less than 1, I guess, at every step, right? Otherwise, I mean, if
they're not going to be multiplied by fixed constant less than 1. That would be, I think, too ambitious. But I'll describe what's.
Okay, I'm just pointing out that it needs to improve, not to weak, right? It needs to get better as the.
It does, but it doesn't need to. But during epoch 2, it really can't expect to get better than the lower bound, the epsilon 2. So all I'm going to do is effectively get an improved interpolation, where it gets dragged closer to the lower of the two epsilons than you would expect, and that turns out to be enough after recursive composition. So it looks like this. We have this special steepener property, and the steepener is, as you see in this picture, steepening the downhill to the next successive defect bound. All right, and then we have this new profile with one more data point. So whereas the old algorithm had p epochs, we now have p plus 1. And this is our new profile going forward. We repeat this process recursively. Okay, so how do we accomplish this? The algorithm, the outer algorithm, it uses the current certified lower bounds, as I say, to choose the next subtree to advance. And every phase is handled in this unified way described here. So I talk about algorithms with baseline advice for the top level base case value L. So at this stage, I'm going to be using L, and we're going to be focusing on the top level, which is also a constant size base case. So these algorithms have both an unseen input, which I'm going to use Y for, and they also have a baseline advice vector, which is pointwise at most the input. And we're going to make all of the queries to Y in some order. And this just corresponds in our application to the setting where xj is the approximation to the true MA value of the jth subtree after epoch R, and then yj is the next epoch, lower bound. And so I'll use little zj to be the true hidden value for that subtree. Does this make sense? So the notation or the letters used in this slide are going to recur. So just we have this image of x, the x's, the y's, and then the z's, which is the ground truth, or the true values on these subtrees. So the x is freely, let me just say that the x is seen by the algorithm, and it's used to decide which bits of y to look at next. And because of the fact that we have these epoch profiles, these progress profiles, and we have some assumed goodness on our inductively built algorithms. And because of the fact that we are using separate fresh randomness on each of the parallel subroutines, we have some nice natural statistical properties of these input vectors, x and y, that we can state as just a general probabilistic model. And that's described in this notion of ensembles. So we have these vectors, x at most y at most z. The x's and the y's are random variables. This reflects the fact that we have a randomized algorithm inductively. and each xj, yj is independent of the other coordinates, but not of each other. So xj and yj can be dependent. Xj is alpha close in expectation to the ground truth, to the true MA value. And yj is beta close, where beta is a little bit better. So our main objective for the outer algorithm, or for this algorithm using baseline advice, is to get as large as possible a certified MAL value of the hybrid input or hybrid view after you start with the baseline of X and you make some n-e queries to Y. So we're going to make most of the queries to Y. We're going to make n minus on the order of root n of the queries. And again, this is chosen, as Avi suggests, so that we have enough information to make at least one intelligent decision. Why we have to let it be root n and not say 1 is a little bit more subtle, but it's it falls out of making things work. Okay. So let's use V here to be the certified MA value of the hybrid input after we make n-e queries to Y over baseline X. And we'll say that Q is a steepener algorithm if we get the following kind of expectation bound over the randomness in both the algorithm and in the inputs X and Y. So the output, the certified lower bound at this critical moment after n-e queries are made should be, as I said, it's going to be an interpolation or weighted average between alpha and beta, between the goodness bounds assumed at the rth and the r plus first epochs. But it's just a little bit better than you'd expect. It's just a little bit more weighted towards the smaller value beta. And that's expressed by this small absolute constant c in this expression. And I'm interested in algorithms which do this for any such x, y, and z. So my base case, this steepener concept, actually needs to work and be analyzable on this infinite variety of different input random variables. So the base case becomes more rich, let's say. So repeating the statement, the upshot is I essentially give such a steepener when capital N is a sufficiently large constant. But there's a significant catch that makes things a little bit more technically difficult. So it turns out that to do the analysis, and I tend to think this is intrinsic, although I don't have time to discuss why. Instead of merely assuming that the bounds are in expectation, that we have these expected defect bounds after R epochs of the inner algorithm, we need to assume a so-called moment bound or exponential moment bound, where we say that the expected value of e to the some multiple of the defect is itself small. So this is a concentration bound. And moreover, to make the analysis work, the constant in the exponent needs to be reasonably large compared to the gap between the two quality measures, alpha and beta, that I'm interpolating between. So we need concentration on our subroutine and not merely goodness and expectation. On the plus side, if we make such an assumption, and we will, as a payoff, we can prove a similar bound for the output value. We can say that the MA value of the output is similarly concentrated, where the constant, the parameter s in the exponent, actually grows by a roughly root n factor. So the estimates get progressively more concentrated with higher recursion depth. And this is important because smaller gaps between quality do appear at higher levels of recursion. Okay, and actually the reason that I choose the number of queries to be n minus root n and not n minus 1 is to make sure that the gaps don't get too small too fast. Okay, so if you look at, when we saw these pictures of these improved interpolation, it's not immediately obvious that you get a sequence of progressively better algorithms this way, but you do. You can see this after a few stages of recursion. And moreover, you can use Bernoulli sum tail probabilities to characterize the values, both of the values t, like the particular time values when the epochs end, and the epsilon values, so how big the error is at these times. And so we end up getting Bernoulli sum tail probabilities with two different parameters describing the two, the times and the errors. And so by a careful just inspection, you can find an epoch for large K where the query fraction and the defect bound are both simultaneously very small. And that's the end of the story, in the sense that you can simply, for such algorithms, you can simply halt after that number of epochs with a good output estimate. Okay, so I want to sketch in what little time I don't have how the steepener concept is built, what ideas go into the construction of steepeners. So first, let me briefly mention a basic characterization of the MA value. I've given here an example computation, and I've highlighted in red some critical edges. So you can see here that the left sub input is basically determining or forcing the MA value to be at least what it turns out to be. We have like the top level has a left dominant child, if you will. And these red edges that I've highlighted, they determine a subset of inputs. So the index set describing these inputs is called an M tree. It's of size square root of n, where n is the input size. So it's quadratically smaller. And this set corresponds to a set that we can force in the game perspective, we can force the output to be in one of square root of n possible outcomes, where the control we don't have is in the random player. So this M tree corresponds to a particular player one strategy for the game. And it's a basic fact that the MA value is the maximization of the average over the M tree, where you maximize over all possible M trees. Okay. So we keep in mind that this is a way of re-expressing the problem in terms of a single max and a single average, but over this richer set of subsets.
So this, these entries correspond to what would be the min terms of the Boolean functions. These are.
Yep, exactly.
Yeah, okay.
Exactly. So what does the steepener algorithm do? In brief, the query order is semi-random, and it makes just one adaptive query to y at this critical step, the n-eth step that I've chosen to be the endpoint of my new epoch in the composed algorithm. So it's choosing between two options. So I have seen most of y, and now either I'm going to look at yi or I'm going to look at yj. You can think of I and j as being random here, except that they are constrained to live on opposite sides of the input. And typically, most of the time, at most one of these queries will raise the MA value of this hybrid input of our current certified lower bound, and we're interested in making a good decision. So to distinguish which one of these two is more promising, and make a good choice, I want to briefly suggest a general study of the effect of coordinate decrements, or equivalently increments, on an MA formula. So if I have an input u, and I take it to a u prime where I've just decremented the ith coordinate down to some u prime of I, what happens in the formula? So in the application, you can think of u prime as being the hybrid view before we decide to make a critical query to yi, and we're interested in what do we gain by this query, or alternatively, what do we lose by failing to make it? And the important case for our analysis is when exactly one of these I and j lives in the optimal M tree for the true values of MA on the subtrees. Does that make sense? So in brief, I study paths in this MA formula. And I say that a path is dominant for a certain max gate that it passes through if it passes from G to its larger input value, strictly larger. And a totally dominant PI is one where it's dominant at every max step. So a basic fact is that the decrement from U to U prime only reduces the MA value if PI is totally dominant. So it's only these paths that we are really concerned about missing, right, by failing to query at this ith value at the critical step. I will also say that a max gate is delta decisive if for its left and right input gate values, there is a gap. So there's an unbalance. And the one of the two is a multiple of delta bigger than the other. But I normalize this in the following way, depending on the depth or the distance to the input variables. And this normalization is chosen such that, well, I think I'll say first, it's chosen as normalization such that when you decrement an input coordinate, it's going to be decrementing, and that input coordinate is totally dominant, it's going to be decrementing the decisiveness values along the path by the same amount. So it's a way in which the levels can be made to look uniform in analysis. Also, if you take a totally dominant path and you start decrementing the input value there, it's going to start decrementing the output value of the formula. So you're going to start losing value, but only for a small decrement. So once you can imagine you start decrementing, the output value is going to start dropping for a while until one of the max gates along this path ceases to be dominant. And then you will stop losing value at the output. So there's a bottleneck that appears, and we can say that the loss of MA value is at most proportional to the minimum decisiveness that appears along the path. I'll show a picture too. Okay, here's a picture. So I'm focusing on this middle M gate, which is at a distance D from the input UI. Let's say that the value here is 0.04. We have a totally dominant path to UI. And the decisiveness, right, is proportional to the gap between this 0.04 and this 0.03. If I decrement this UI by a sufficiently small value, the value at this M gate goes down by alpha over 2 to the D over 2, whereas the decisiveness is normalized to go down by alpha. And here, not alpha, theta. And here theta is sufficiently small that everything that was on this path and formerly dominant stays dominant in this process. The same thing is happening up at the top, except until we hit a bottleneck of the sort that I described. All right. And I truly am almost done. So I'll try to wrap up. So along this path, there are decisiveness values for each of the max gates. If we look at a totally dominant path PI, I'm going to order them as D1 as decisiveness 1 up to decisiveness L. This is not in the order that they appear along the path, but it's in sorted order. And a crucial part of the analysis is to basically compare the minimum such value, decisiveness 1, which, as I've said, is a bottleneck on how much we can lose from a decrement. It's a sort of bottleneck on like how much risk there is from a failure to query this coordinate. And we also consider a near median value, dec at 0.4 L, where L is the number of these things. On the one hand, if the gap between the two is fairly large, then as you start decrementing UI, let's see. There are two options. Either you don't make a decrement which is as large as this 0.4 ELF, this near median value. And if you don't make a very large decrement, then this path remains dominant and at least a 0.6 fraction of its max gates. And then that's like a special trace, a special property of this path, which is not true of most paths in the tree, in the overall formula. And the other option is that if you do make a large decrement, large enough to cause at least a 0.4 fraction of these formerly dominant gates to become non-dominant on this PI, then there's this intermediate period. If you think of the decrement as happening gradually over time, then there's a period of time in which the further decrement is not leading to a decrease in output value because it's hit this bottleneck that I mentioned. So in the remaining case, when the decrement is enough to destroy dominance at nearly half of the max gates, then the loss in the output value is significantly less than we might pessimistically worry it could be. So again, these two options leave either a trace that marks this path I as special and therefore perhaps worthy of a query, or in option 2, we get a free pass or a reason in the analysis why a failure to query here is less bad than it might otherwise be. So they're both good for our analysis, and this is a kind of win-win. On the other hand, if this gap that I talked about between the near median and the minimum decisiveness is small, and small compared to the minimum itself, and if, furthermore, this holds for most totally dominant paths on our input, which is the only case that's bad enough or worrisome enough for us to have to focus on, then we get another type of win-win-win. So either the same type of thing happens as before, or there's this third kind of special configuration that appears, where you have these many so-called pendant gates, pendant max gates hanging off of the path PI, whose decisiveness values are all similar to each other and much larger than the decisiveness values appearing on non-dominant gates of this path on the decremented input. And I know this is a lot to digest, but let me just say that this is a win-win-win. And I'm focusing here on a case of something that happens for most paths. So we use an analysis of random walks at this stage. And briefly and pictorially speaking, it looks like this. So I'm drawing the space of all totally dominant paths on the input U. And I'm saying, let us suppose that for most of these paths, the decisiveness for many gates, many max gates along the path is roughly equal to the minimum decisiveness along the path. So here's one such path in our space, and here's another. And in each case, this property holds. Well, if this holds for most of the trees, most of the paths, then random walks analysis shows that actually it's on account of some pervasive common value of the decisiveness that appears all around in this on random walks through most of the space of totally dominant paths on U. There's this pervasive common value, and so what happens is that if you take a typical path I, which is totally dominant, not only will this pervasive value occur as a decisiveness value many times along the path, but it will also appear many times hanging off the path like this. And so then what we study is the effect of a large decrement along this path, and thinking about the residue that remains after the decrement and comparing it to this similar value, which is found many times hanging off the path, and saying that there's a third type of special condition that you cannot expect to see on a typical random path in the larger full tree. So there's a second type of special configuration that appears, marking this as worthy of a query in our recursive scheme for our steepener. So the steepener algorithm on this critical query to yi or yj, it looks for signs that pi is special on the current hybrid input. If so, it chooses I, otherwise j by default. And so I'll just briefly say that the moment bounds seem to be critical for the win-win type disjunctive analysis that I mentioned, to have the right quantitative force to it, that you can combine our conclusions on the different possibilities and in expectation. Okay, so in conclusion, games against nature are an expressive model of decision-making under ongoing and persistent uncertainty, where we're making successive observations of nature, and we at least are able to confidently assume some kind of statistical model of nature. We give an exponential savings in the natural case of fully alternating binary moves. And there are many avenues remaining for study, the most evident being to improve the speed up, to reduce the space usage if possible, and to find other applications of these kinds of techniques. So thank you, and I will welcome any questions.
Yeah, thanks a lot, Andy. Questions to Andy?
I have
Moni.
a question. Oh,
Sorry.
somebody else?
I don't know which.
All right, I'll go.
Either one.
Everyone-
Either one. Sure. Go ahead, Tony.
Yeah, so this might not be the most well-posed question, but I was wondering if for the fully alternating case, if you have thought at all about restricted lower bounds, like for the same type of algorithm that this family of algorithms that I guess it's
Right.
like some kind of query model.
Yeah, so I have, so far without success, but it does interest me. So let me acknowledge, and maybe I should have said this earlier, but the basic situation for games against nature is still less well understood than for adversarial play. In particular, I don't know whether this problem is easier or harder than the adversarial play version, because as far as I know, the right constant in the exponent, so 2 to the Cn,
Right.
C is just somewhere
I mean,
between 0.5 and 1. Or it's less than 1, but only a little bit less than 1 as far as I know. So yeah, it would be great to prove a C equals 0.51 lower bound. I just haven't succeeded in doing so.
That there's no lower bound? Not even?
Well,
must
2
be
to the
some-
0.5 n follows from kind of the needle in the haystack
Oh,
idea. Yeah.
Oh,
So
yeah,
that's
but that's, no, but in the case where you don't, sorry, the needle in the haystack came in when you had that that there could be very low probability, right? The additive.
yeah. So there's two. Maybe I could say there's two types of needles.
Yeah,
There's
so
a really
let's
a thin needle and a thick needle. So the
Oh.
needle that I'm talking about here is a thick needle, which is the size of a whole M tree, but it's a
okay.
hidden M tree. So
Okay.
it takes on the order of root n queries to find a hidden M tree
Right.
where I have ones all over that M tree. And that's all that I'm pointing to. So that's the only lower bound. It's not very interesting.
I
It's a
see. Gotcha.
non-deterministic lower bound, really.
Yes. That's right. I mean, I have to think about what an approximation, what the right notion of non-deterministic lower bound for approximation problems is. But yes, essentially, even to certify, right, the approximate lower bound, you need on the order of root n.
Yeah, certification. Yeah.
Yeah.
But whether 0.51 is possible, I tend to think that it may be, but I haven't done it. Yeah.
Other question?
Can I ask a question?
Of course.
Hi.
Hi, Amir.
So, I'm not sure that I completely understood everything, but is there some characterization of the type of operations you capture here? If you replace maximum by some other operation or average by some other operation, it seems that the scheme you generated is quite general. What?
Well, I think that there definitely is scope for further progress of this type. Rahul also has had some ideas and initial observations in this direction. I guess I would file that under other applications of our algorithmic and analytic techniques. It was a lot of work to get the result to work formally just under the max and average fully alternating. So I haven't attempted a formal generalization, but I definitely think that this style of recursive improvement, has potential beyond the specific problem.
Maybe this is related to Amir's question about generalization. I'm just wondering if there's any sort of new probabilistic inequalities that are clean, that you needed to generate for the analysis, but you can write down without this application, like what is eventually driving the inductive proof of the moment upper bound.
Yeah, so I mean, I do prove at least one custom probabilistic statement in the course of doing this work, along with using plenty of standard sort of concentration inequalities. There's something called this UV savings lemma in the paper but it's also, it seems fairly hyper specific. So whether this type of result could follow from something more transparently elegant, or beautiful, and that would itself have value. I would love to see something like that.
Yeah, but I asked whether you generated something like this. So you don't, it's still specific to the analysis.
It's specific to the analysis, I would say. Mm-hmm.
Okay. More questions? All right, great. Thanks, Andy.
Thank you all very much. And thanks for the opportunity again.